Ehsan, and I'm in the second year of my PhD at Chalmers University of Technology. I'm talking mainly about biocomposites today. So an overview, I will have a background and introduction about from fiber to composites, and then I will mainly talk about my first two projects. Firstly, surface modification using additives, and especially molybdenum disulfide. It's so interesting. And the second one, hydrophobization of fibers by AKD derivatives, and the future plan at the end. So from fiber to composite, what is the general goal actually? Reduction of oil resource products and making a composite that is affordable. The affordability is so important here for us because if it's not affordable, always it will be in the lab and it doesn't go to the industry. So what is my magic material? Here it is thermomechanical pulp. And thermomechanical pulp, basically it is just trees that is thermally and mechanically processed, and it is one of the cheapest material. It's content of cellulose, lignin, and hemicellulose. Here in this picture you can see the fibers. The second one, it is a SEM picture of the fibers that is taken by me, and the third one you can see an optical microscopy picture, and as you can see, the fibers are a mix of really cellulose, hemicellulose, and lignin, and it is not really separated, and it is so mixed. And what is the aim here? Producing a composite consisting more than 70% weight percent of TMP actually. And the requirement for that is we have a good mixing between this thermomechanical pulp and the matrix that can be polyethylene or polypropylene, and have a processability in a commercial scale. So at the end of my PhD, I'm aiming for the kilo scale, but now we are talking about ton scale at the end. And my material, my composite, should be thermally stable during processing, for example, the extrusion, or at the end product also. And at the end, having very good mechanical properties, at least as good as existing commercial products. So we have used mainly two methods, firstly using additives, and the second one, chemical modification of fiber surface. Here I have a brief introduction to the process of, so these equipments that we are using at Chalmers in the lab scale process, we have a mini twin extruder that we can put like 2 grams in one batch, and here you can see a product of that. And in the pilot scale that is available in the material engineering department, we have a compression molder that we can have about 10 to 12 grams of material that is 10 centimeter to 10 centimeter product at the end. And at the end, we have a twin extruder that we can feed 10 to 15 kilograms per hour. And then the additives. So I've talked about molybdenum disulfide, but it is interesting, molybdenum disulfide, it's inorganic and we are using it for like forestry product, but why? Molybdenum disulfide already is used in oil and engine industry as a lubricant. Actually, it has been shown in the literature that molybdenum disulfide coordinating with aromatic structure, and guess what? In TMP, we have high lignin content, and lignin has a lot of aromatic parts in the structure. So we said, why not? It's a good idea, perhaps. So in the method, we have used two different types of fibers, TMP or DP, dissolving pulp, as a reference because dissolving pulp is about 95% cellulose, and two kinds of additives, molybdenum disulfide and magnesium stearate. Magnesium stearate, again, as a reference because it's already used in the pharmaceutical industry, and EAA, or ethylene acrylic acid copolymer, as the polymer. And we were mixed it in water and then compression molded it. And you can see two examples here. And the analysis techniques, we did IR, TGA, tensile tests, DMA, impact strengths, SEM images, and EDX analysis at the end. So some very brief results here. We can say from the tensile test that we had the highest strength in the 70% of DP or TMP. And actually from the DMA test, we found out that the additives has a very positive effect on the mixing of the fiber and the polymer actually. From the EDX analysis that I will show you in the next page, it is confirmed our theory that the concentration of molybdenum and sulfide, the peak intensity was much higher in the TMP-based samples. And at the end, we said, why not we use a combination of both additives, both magnesium stearate and the molybdenum disulfide in the samples. And it was interesting that we had a very positive effect on the DP-based biocomposites. We had a positive effect on the TMP ones also, and we had a better mechanical property, but it wasn't that much comparing to DP. So here you can see the EDX analysis. We said, okay, lignin has some aromatic parts, so molybdenum disulfide should go to have a better like interaction with the TMP than the DP. So here you can see that we have a very high intensity peak of molybdenum in the TMP samples, TMP composites. But then here we have a very low like intensity of molybdenum on the DP-based samples, and actually our theory was somehow confirmed here. And what is the main conclusion about this first project? So molybdenum disulfide has a potential as a lubricant for TMP fibers and the forestry products in the future. And the second method for have a better mixing between the TMP fibers and the polymer is surface modification of fibers by AKD or alkyl diketens that is used a lot in the industry actually, and it is the structure here, you can see it. But the problem is that the existing commercial AKDs are a mix of different AKDs and different length of carbon chains. But for my research, I need to have a like AKD that I know exactly how many carbon chain I have. And then, so we have synthesized different AKDs, for example, from lauryl chloride, or we have synthesized stearyl chloride from stearic acid, and then we made a AKD from that. So the general way in the literature using triethylamine and diethyl ether as a solvent was not really reproducible. So we played around the reaction a bit. We played by adding a base or changing the solvent. And actually we used mostly the solvent here, and we changed the solvent to butyl acetate. And briefly, the reaction was happening 2 hours in 50 degrees. And we have a reproducible actually product. Here you can see an example of the reaction. So here we have cellulose that we have an OH group, and we have a reaction between this OH group and the AKD, and the AKD will open and gives us this product that because of the R chains, it is more hydrophobic, and the conformation is about the IR peaks here. You can see these 2 peaks here. It is the carbonyl peaks actually that is confirmed that our reaction has worked. And then taking the AKD modified fibers one step further. This reaction that I showed you has been used a lot in the industry, but what is new here? So we said, okay, why not make it more even hydrophobic? We have these carbonyl groups, and we make another reactions actually that we put some carbon chains on the oxygens here, on the carbonyl groups. And we did this reaction, and again, it is confirmed by IR here, you can see, because the carbonyl groups in the reaction has decreased a lot. So you can say that we have that carbon chains. So basically making more hydrophobic and have a better mixing in the in our composite. So finally, my last slide, what is the next steps? Actually finding a reliable method to calculate surface energy and the degree of hydrophobicity of modified TMP fibers, because it's so hard to like measure the contact angle on the TMP sheets. It is so porous and the degree of the roughness. So we should find a reliable method for that, and coordinating the best chemical modification with the matrix, because it needs to be the surface energy needs to be enough close to the matrix, either polyethylene or polypropylene. And then extrude modified TMP and the matrix with different weight percentage in the mini extruder after we find the best like chemical modification in this case. And then analyzing the mechanical properties via tensile test and DMA to see that the mechanical properties is good enough or it is strong enough. And then finding a relationship between finding a reliable method also to do the rheology, because it's so important for the extrusion process. Actually, we need to have some information about the rheology. And then at the end, finding a relationship between different chemical modification and final mechanical properties and the flowability of the composite actually in the extruder via multivariate analysis. So we can say this chemical modification has a better probability in the extruder at the end, adapting the reaction of chemical modification to industrial purposes, because it needs to be a green solvent, it needs to be fast and continuous reaction, and the temperature shouldn't be really that high because it makes our product so expensive. And then at the end of my PhD, I think scaling up the process. And here special thanks to my supervisor, Gunnar Westman, and Abhijit Bikandesh, that we had a very good collaboration on my first project. He's a PhD student at IMS, Industrial Material Engineering at Chalmers. And finally, Bioinnovation and Stora Enso for funding my project, actually, and all of the researchers and engineers at Hilta and NACA facilities from Stora Enso that give me a lot of good comments and consultants normally. So thank you to you for listening.